Hello everyone. Today we have Sanchayan Bhowal from math first year. He is interested in probability theory and statistics, and today he will give a talk on estimation in tensor Curie-Weiss Tensor model based on his joint work with Professor Shomon Mukherjee. Over to you, Sanchayan.
Okay, so as I have mentioned in my abstract about spin glasses model, so before actually going to the uh, actual stuff, we'll see what is a spin glass model. So we'll we'll gradually understand all the 5 words in the title. So let's start with spin glass model. Even before that, we'll look at a classic example of the Ising model. So this will help us to motivate the definition of spin glass model. So in Ising model, you have a graph, and in this graph, G equals to B to E. In each of these vertices, you put some magnets. So magnets, and in each of these magnets now has some north pole and south pole. So we'll just observe it from the top. So we are only interested in the spin or the pole in the top. So we will label north with +1 and south with -1. So +1, -1, +1, +1. So each of these vertices now have either +1 or -1. Now what we do is we make this +1 and -1 random. So that is in the whole configuration, in each of these vertices can take +1 and -1. In this whole configuration we put a probability distribution. So what is the sample space? The sample space is sigma in -1, 1 n. So this sigma is the configuration. So this just shows that in each of these vertices there is a +1 or -1, and we give a probability distribution to this, and we write it as beta j sigma I. Okay. So this beta is a parameter, and in physics literature this beta is actually the inverse temperature. So what does this mean? So in order to get the intuitive understanding, if you have high temperature, so this just means that beta is very small. So in that case, this one becomes very close to 1. So this means this whole probability distribution is quite a bit like uniform. So this means it's highly random, like everything is almost equally possible. Whereas if temperature is very small, then this beta is very high. In those cases, it favors all those configurations where this thing is positive. So that just means that it favors all those things where in the edges, the adjacent positions, we have same sign. So if you have same signs, this will be positive, and we will get those things with high probability. Because if it's negative, then this beta is huge, then it will almost be close to 0. So those configurations are less likely. So but you can just think it as of a definition of a probability distribution. We will only be interested in that. Anyway, so now this thing can be written in a different way. Well, sum over all ij, and I will put aij. What is this aij? This aij is basically the adjacency matrix of the graph. So you can see that if I is j, then 1 will come here and will add only on those points. But what is special about aij? We can put anything, and that's what gives us spin glass. So spin glass sigma proportional to xp summation ij jij. Now this jij is any matrix. It needn't be a 1 0 matrix. It can be anything, 2 3, any value. It can take fractional values, anything. And notice one thing, from the beginning only I've been writing proportional signs, because there has to be a normalizing constant. So how do you find the normalizing constant? You need this probability measure to sum up to 1. So you just sum up to 1 and divide by that thing. You sum everything over all the sample space and divide by that thing, so you will get some normalizing constants. I'm not writing that here. Anyway, so what we see now is, in each vertex we are putting either plus ones or minus ones. But what's stopping us to put more such values? We can put q many values. We can put like thousands and 10,000s of values. So we'll do that now. And what we do is, we take any x from q to the power n, and this q is basically this vector 1, 2, q. I could have put any kind of thing. I just chosen the first few natural numbers, but it's okay. You can put any colors. So this kind of things, like it's putting colors on each vertices. And now you take this distribution is proportional to xp beta summation ij jij indicator xi equals to x. So this is just the generalization of the spin glass model. So here we had only sigma belonging to -1 to sigma in -1, 1 to the power n, whereas here x belongs to this thing. So in each vertex you are putting a color, and this color ranges from 1 to q. So and this is called Potts model. Now we understand two more words of our title. Now we will extend this Potts model further. How do we do that? We take this jij and replace this jij with a p tensor, that is numbers indexed by p many things. Here the numbers were indexed by two things. Here we will index the numbers by p many things. So with more possible ways, and then we do it similarly, proportional to exp beta summation I1 to IP beta. Okay. So sometimes what happens is, apart from this beta parameter, we introduce a bias term. So and that bias term is called the magnetic field, and that's what we will do here. I'll put a additional bias term, this h times indicate. Is it visible here? So what is this putting? So what is this h doing? This h is putting a bias on the vertices which is colored 1. Now you can ask, you could have put bias to any number. You could have put to 2, 3, q, anything. But I have put only to 1, and for simplicity reasons. And you could have put different bias to different colors. That is also possible, but again that will even complicate our problem. And you will see why this putting only one bias helps. Okay, but and now I will put the normalizing constant, write it as q to the power n and zn beta h. This is also known as the partition function. Again, for some physical reasons, don't ask me why. So this is the partition function. Sometimes people don't write this q to the power n. In that case, q to the power n gets absorbed in the partition functions. And here we are just writing q to the power n. It doesn't matter much. And in the whole lecture, I may sometimes replace n by n. So you just take n equals to capital N. Okay. Now, even solving this problem, solving questions about this problem is very difficult because of this general matrix, not matrix, tensor. Even this is difficult, this is even harder, and this is called the tensor Potts model. So, we will take a special case. How do you do that? So if you had taken this G, and if you had taken it to be Kn, let's say, how will this thing look? This will look like 1 by 1, where I not equals to j, right? So basically the adjacency looks like 0, 0, 1, 1. Just to make it look nicer, we put self edges also, and in that case this one becomes 1, and you will see that it actually doesn't matter much if we put self edges or not. So you have this matrix. Consider the Kn graph to also contain self edges. So sometimes in order to make the row sum 1 for some special regions, you always normalize it by n. So now this is called the Curie-Weiss setting. In that case, everything is put to 1 by n. So what will be the corresponding version in the tensor? In the tensor, instead of 1 by n, we will put 1 by n to the power p minus 1. So we will write j I1 to ip equals to, and now this distribution becomes probability x equals to 1 by q to the power n zn beta comma h exp. Okay, so this is the our now probability distribution. No, here you see the it is a matrix, and the p equals is here p equals to 2. So what is the value over here? 1 by n, right? So basically 2 minus 1 n. So you need this sum to be 1. That's why. Okay, and here you take all the sums, and then one important thing where this beta and h lie. So as I have already mentioned, all this comes from the physics motivation, and this is the inverse of temperature. So beta is taken to be positive. So and h you can take negative also, but it doesn't matter much. So we'll just restrict it to non-negative regions. So and this is our parameter space. Now I will write this in a different way. So I will define few variables. So I will write xi r equals to indicator xi equals to r, and xr is the xr bar rather mean number of vertices colored r. So you just think it as of a intuition because there is no vertex as of here in the tensor case. So you sum over, and then you take this vector x bar and put all these xr's over here, and we call this magnetization vector. Okay. So now we will rewrite this distribution. So probability x is 1 by q to the power n zn h beta n summation r equals to 1 to k n h. Okay. So sometimes it's easier to look it as just the pth norm, pth power of the pth norm. So we'll write it like that. and where this x bar belongs to r cube. But note that this x bar cannot take all the values of r cube. So first of all, everything has to be positive, and second of all, not negative, and second of all, the sum has to be equal to 1. That is also clear. So this belongs to, write it as h cube, and even here it takes a subset of values. It only takes those values which has this n in the denominator, kind of something. Okay, now we are coming to the statistical picture. So now what is this x bar? This x bar is the sufficient statistic. And studying sufficient statistics is very important, because if we study that, we can study many estimators and many statistics. Okay, so once we have this, what are our parameters? So our parameters is beta and h, and now our motivation goes to estimating them. So we are interested in beta hat and h hat, and I am writing a script n because it depends on n, and n is the dimension sort of thing. So write it as, and I take the Emily estimate beta with h. As you see here, on important step I have taken, when I am estimating one, I am taking the other thing to be known. So why not simultaneously estimate both of them? But actually that's not possible. We will show that not even possible for Emily case. For other cases it might be possible. For Emily you have to take one to be known. So we got two estimators. Now we will ask the question. Question: asymptotics of beta n hat and h n hat. So how does this beta n hat and h n hat vary for large n? Note one important thing, this n is not the sample size. The sample is 1 for us. The sample size is 1. This n is the kind of some sort of dimension. So what do you mean by asymptotics? So asymptotics you mean like convergence laws, like weak laws or CLTs for beta n hat and h n hat with respect to n. So right here, weak laws. Now you will see why I have written CLTs over here, not just CLT. And in order to do so, in order to find the asymptotics of beta n hat and h n hat, we need to find the asymptotics of the sufficient statistic. And once you find this, once you have a complete picture of the x n hat, you will see that the other things follow quite a bit easily. But this x n, the asymptotics of x n bar is itself quite difficult because of this z n beta h. Because we have no clue about how this z n beta h looks. If we had any sort of nice looking function, we could have just taken the log and we could have taken the derivative, and it would have been just be an easy optimization problem. But the issue is this z n. We have no idea about this. So let's see how can you now estimate this. Estimate as in approximate this, not the estimate in terms of statistical manner. So this is our primary question. This is on the top. Okay. So lemma. So now you see that even though Zn is difficult to approximate, so what we do, we put this value here and we approximate this together. How do you do that? And we do it like this. Sambar equals to V beta H equals to big O of big theta rather n to the power minus q minus 1 by 2 e to the power n h beta h. Okay. So here comes a new function now. So h beta h is t is beta pth norm power p h times t1 minus summation p 1 to. Again, this v is only for those v where this probability is non-zero, because if this is 0 then it's useless. So you just take v to be all those things which are possible in this hq. Anyway, now this function, so now everything boils down to studying this function. So if we have a good idea of how this function behaves in different parameter space, we have a very nice idea about how the probability distribution behaves. So, and this is in, again in some physics terms, this is called the canonical free energy. Okay. So now I will state the weak law. Of course, I won't go to the proof, but if you see the weak law, then you will understand why do we need to study this h beta h. So theorem. So it might look a bit convoluted, but it's not so non-trivial. Okay. So what this m beta h means? This m beta h means the set of maximizers of h beta h. Set of maximizers of h. Hmm. 2 2. There's no z. Just the z is here. Okay. So this shows that this xn bar approaches the maximizers. Now there can be many such maximizers. So that's why you take the set of the maximizers and you calculate the minimum distance, and you show that that is exponentially small for beta n going to beta and h n going to h. And this is our weak law. So now you know that you need to study the maximizers of h beta h, because if you study, because you need to have a good picture of the how the maximizers behave in order to get more asymptotics of xn bar. And now comes important definition. Okay. So here is the parameter space. That is, I take x-axis, in x-axis I take beta, and in y-axis I take h. And then take a point here, beta c comma 0. I'll name this beta pq tilde h pq tilde, and this is a curve, continuous curve, and this is beta comma phi of beta pq. Okay, so what does this mean? So in this, so this is our parameter space. So h is from 0 close to infinity, and beta is from 0 open to infinity. Okay. So this region, apart from this whole thing, the shaded region here, h beta h has one maximizer. Right, just one maximizer. Not only that, the Hessian of the h beta h is negative definite. And in this region, from beta critical containing beta critical, and this region here, h beta h has q plus 1 maximizers. And in this region, open here to open here, I mean this curve, but not taking the two endpoints, here h has, oh sorry, h has two maximizers. Now one point is remaining, that is this point. This is indeed a very special point, because this is the only point where it has one maximizer, but the Hessian is negative semi-definite. Negative semi. Okay. So this is the complete picture of our parameter space, although it's not quite complete, and I will define something which will help us to complete the picture. So we will call this thing, we call the shaded region regular points, and we, wherever h beta has more than one maximizer, we call it critical points. So this one, these two critical, and this is quite a bit special, so we'll just name this special point. Okay. And this phi is continuous and monotonic. Okay. Now comes the important lemma. The maximizers of h beta h let's say m looks like this thing. Basically, you can parameterize the maximizers, and this is quite strong. This is where we extensively use the fact that we put a bias only on the first term. If we had put many such biases, then this thing wouldn't have been possible. That this parameterization, and this parameterization gives us a very powerful tool, because now everything boils down, if the whole optimization problem boils down to one dimensional optimization, and we can easily perform one dimensional optimization. So now if you define this function k of x to be beta x to the power b minus x log x, then finding the maximizer of h beta is equivalent to finding, if we just put this thing in h beta h, so that becomes a single variable function on s, and we will only maximize this. So, and we'll name that function f beta h. That is, this is nothing but just putting it nicely. times h. Now we will further classify the special points. So what we do in special points, there are two kinds of special points, type 1 and type 2. So in type 1 we take the fourth derivative and that has to be negative, and in type 2 f beta h fourth derivative has to be 0. And the surprising thing is that this case type 2, the fourth derivative being 0, this only arises when p equals to 2 and q equals to 4. Nowhere else there is no type 2 special point. Only p equals 2 and q equals to 4, there is a type 2 special point, and that is a very specific property of that function. And now we will complete the this partitioning of the parameter space, because we partition the parameter space into regions, regular points, critical points, and special point. What happens when this point is a type 2 special? And that's actually a very easy diagram. Here you have beta, here you have h, and in this region there is q plus 1 maximizers open, here it was closed, and this is the type 2 special point. So basically this whole curve shrinks to this point. So there is no curve here, and there is only one maximizer here, there is q plus 1 maximizer, everywhere else this is regular. So this is now the whole characterization, or the whole parameter partition of the parameter space is complete. And now we come to the CLT, and we'll see that in each of this parameter space, in each of this partition, the CLT will be different. That's why I told that CLTs. So in each of these thing you will get a different CLT. Okay. So I will state the CLTs because it's almost impossible for me to prove. But we will use the CLT in one of the proofs. Okay. See, what happens in regular points? In regular points, you have one maximizer. So I am calling that maximizer m star. So you have n to the power half, and by weak law you know that xn bar is going to m star because that is the only point. So you subtract m star from xn bar, and that goes in distribution to this multivariate normal sigma beta bar p times m star p minus 1 plus h bar. The sigma is a positive definite matrix, and we have a very explicit form of this matrix, but it's quite a long, it will take almost one board for me to write this down, so I am not writing that. And we take this xn bar to be distributed as beta plus beta bar by root n. So in most of the CLTs like that only CLT we have seen, we keep these parameters fixed, but here we are perturbing these parameters by a little bit, and this will be required in the proof of asymptotics of beta n hat and h n hat. That's why we are not just putting b and beta and h to be fixed, we are proving a more general version where we are perturbing it by some number. And if you put beta bar and h bar, you will get it for the normal thing. And in that case, this will become 0. The mean term will be 0. This perturbation is actually put in the mean term. And we not just prove distribution, we also prove that the moments converge. And now let us look at the special points and theorem again. So first type 1. Now here is a thing that's new. In type 1 special point, we get 1 by 4. The correct scaling is 1 by 4. And again there is unique maximizer, so I can put m star d, and here it converges to t beta h times u, where u is a vector and u is 1 minus q 1 1, and this t beta h is a scalar which is distributed as x to the power 4 by 24 times something, I am not writing, it's long, and some mean terms. So here we had a normal distribution. So in normal distribution we have x square and a minus. Here we have x to the power 4 and we have an additional mean term just like this. And in type 2, one important thing, of course, this xn bar here is distributed as probability beta plus beta bar by n to the power 3 by 4 h plus h bar. Again for similar regions we have perturbed it. Now what about type 2? In type 2 you have n to the power 1 by 6 and we take xn bar minus star, and that goes in distribution to fh. U again, and u is the same thing, and fh is distributed as exponential, and again you can guess what will be this be. This will be x to the power 6 by some constant here, of course negative constant, plus some mean term. Now one very important observation is this t depends on both beta and h, I mean beta bar and h bar, but this only depends on h bar. That is a strange thing. And what is this h bar? Again this xn bar is distributed as beta bar by n to the power 5 by 6 . Now you see that I have skipped the critical points. Actually you cannot prove direct CLD for critical points, but because we have many such maximizers in critical points, 2 and sometimes q plus 1. So in those cases this xn bar is kind of confused to approach which of these maximizers. So we cannot give a direct CLT, but what we can give is a conditional CLT. So once we know that it's approaching this maximizer, it will have a CLT behavior just like this. In that case it will once we condition, it will just behave like a regular point, but that conditioning is required. Okay, so any questions? Because now I'll get into the proof of the asymptotics of the MLs. No questions? Yeah. Yes.
So what is the significance of this Q? So like, is it having some special properties in the model, or is it just some constant? Yeah, some constant dependent
Q is
on
the
beta and
number
H?
of colors we have put from the beginning. It
Okay.
was a model choice.
Okay.
Without Q, there is no Potsdam.
Is there any particular significance of this half, 1/4, 1/6,
Yeah.
and so on?
Okay. This was something I was going to tell, but I forgot. Thank you for reminding. Uh, yeah. So why is this 2, 4, and 6 coming? So let's give an intuitive description of this. So what is a maximizer? So if you want to find a maximizer of some function, so you are interested in finding roots of the derivative or gradient. So let's just think it as a one-dimensional thing. So now this root can come in various multiplicities. If it comes in one multiplicity, then the second derivative is non-zero. And in regular point, we know that this Hessian is negative semi-definite. So if you go back to the this f, then this will have the second derivative to be non-zero, and that 2 comes from the second derivatives 2 here. And what happens here? Here it's negative semi-definite, so second derivative is also 0. If first derivative is 0, second derivative is 0, and it's a maximizer, the third derivative has to be 0, and otherwise it will not even be an extremity. So if first, second, third is 0, the multiplicity is at least 3. But in type 1 special point, we know the fourth derivative is non-zero, so that 4 appears here. And what happens in type 2 special point, even the fourth derivative is 0, so fifth derivative also has to be 0. If fifth derivative is 0, now we are asking the question, is sixth derivative is 0 or not, and we will see that this sixth derivative is actually non-zero, and that 6 appears.
Thank you.
Yeah. Okay, so let's now dive into the a few lemmas, again lemmas, that will help us to prove. Should I? Here I will require few properties of the exponential family. So if you just look at this model, I think I don't have the tensor. Oh, it was written. It's not observable. Anyway, so if you remember the this whole definition of the model, then it was just an exponential family, and we exactly know how to find MLEs of exponential family, and that is just solving this equation h. So here we solve this equation with respect to h, considering beta to be known, and here we solve the equation considering h to be known with for beta, and we get the MLE estimate of both. Now the issue is we don't know these expectations. That's the main problem. For that we cannot find the expectation explicitly, and we cannot do many good things that we would have been able to do for some nice enough exponential families. But still we don't lose hope. We continue. Okay. So now comes a lemma. Define this U and P beta H expectation of this thing, basically. And UN1 beta H expectation of, yeah, don't just put p equals to 1 over here, because from the beginning only we have taken p greater than 1, because it starts with a matrix, so p has to be greater than 1. Anyway, and what is the lemma states is this 2 is increasing. And let's look at a proof. The proof is very trivial. So write this function fn. This fn is also known as the log partition function, which is nothing but taking log of the partition. Now again it follows from the properties of the exponential family that if you take the derivative of this function with respect to b, this will come out to be un t of beta. Okay, one important thing, increasing in beta and h respectively. So first one is increasing in beta, second one is increasing in h. H and h. Okay. So now we want to prove these functions to be increasing. So we want the first derivative with respect to beta and the first derivative with respect to h to be greater than 0. And in order to do so, we just need to prove the second derivative of this function with both beta and h is positive. So in order to do that, we just need to prove fn is convex in each of these terms. So, and I'm not going to prove that fn is convex, but it's very easy to prove that fn is convex using Holder's inequality. Use Holder's inequality. And because if you take z and beta h, you can just write it as a summation of whole over the whole sample space, and then you use Holder's inequality and you will get fn to be convex, and that proves that these two functions are increasing. Okay, so now we are in business. We'll start the proof. We'll at least prove it for a special region, that is the regular point. Let's remove this. Okay, this now. Maybe I'll put this on the top. Start here. Theorem. And the statement is that this root 10 times h n hat minus h Gaussian distribution to normal square if beta h double derivative of s. And what is this s now? So this s is the maximizer of f beta h, or basically this, if you take the maximizers, if you so beta and h is fixed here, and m star is basically xs, because you know that m star has to be of the form xs, some xs from that limit, and this is our result. So we will prove this now, and we will see how you use the CLT of the magnetization vector. So we go back to the definition. So we need to see where this goes. So now we'll do a rearrangement. Ability is equal to t plus h, sorry, h plus t by root n. Right. Now we know that un1 is an increasing function in h. So I can put un1 in both sides. Beta, it's equal. Okay. Now, what is this un1? Let's go back to the definition. So it's expectation of respect to beta and h and hat of x1 bar, that is equal to expectation of n h plus t by root n x. Okay. Now what is this? This is the MLE. So you know this solves that equation. So this is nothing but this. So now we subtract m star from the both sides and scale it by root n. T by root n times x1 bar minus h. Okay. So now you see why I proved the perturbed version of the CLT, because now we will use that, because we know that when I stated the CLT, if you notice it carefully that not only I said in distribution but also in moments. So you know that this moment converges, and this moment converges. If it converges, of course, it converges to the moments of the projections of the multivariate normal, because x1 bar is just the projection, first projection. So, and if you carry out the calculations carefully, you'll just see that this is this goes this just goes to probability, and this probability is beta h, beta h, and this one goes to normal 0 comma minus q plus 1 whole square. I think it won't fit here. So this thing goes to q beta h normal 0 minus q minus 1 whole square f beta h s less than equal to. This is some calculation, and once we have that, we just use some property subnormal to get this. This is equal to probability beta h normal 0 minus q square q 1 square. Okay. And this is the CDF of our testing. So this in distribution goes to. So we prove the asymptotic of h and hat, and similarly you can prove the asymptotic of beta and hat also. The only thing that will change is this un1, instead of un1 we will have unp, and for that you need to prove this CLT by taking norms. That is also easy, that is nothing difficult. And so this is the proof only for regular points. Important thing, regular points, of course, because we are using the CLT of regular points. Now if you just look into the proof, everything follows for the special points. Nothing is special about regular points. So you just go on, look at the proof. You will just scale it by a different thing, and you will get this. Of course, you will get some different distribution, but you can exactly trace the this thing steps. But what about critical points? And for critical points, we don't even know the direct CLT. We know conditional CLT. In that case, you need to condition on more such stuff, and it's a bit of involved thing. So I'm not going to go into that. Yeah, I think I was in time. So that's it more or less. Thanks for coming. Any questions?
Okay, if there is no question, we stop today. Thank you, Shanchandra, for this talk.